So this is our equation to be solved, and let us try to generalize our Fourier transformation approach in the following way. So here, instead of integrating over momenta which are located on the real axis and with complex exponential, we allow independent variable which parameterizes the contour of integration to be arbitrarily complex. So this is the main tool in all this technique, and proper choice of the contour will be one of the most important ingredients in the method of solution. So, and here, instead of our function of x, we introduced function of z of t. And let us now substitute the solution in this form to our original integration differential equation. And in our transformations, we will just make use of the fact that the contour is chosen in such a way that the integral is well defined along this contour. So, substituting this to our original equation, we arrive to with the requirement of this integral over the contour t, over the contour c, over dt to vanish. It is actually convenient to slightly rearrange the expression in the square brackets to the following form. And in fact, this object will be very important, and we will introduce shorthand notations for them, so that the equation actually becomes even simpler. So now we are going to simplify our life and to see. So, because in the end, you know that the only independent function in this solution, which actually is some other representation of the unknown function y, is z of t. And in fact, this equation, which looks like an integral equation, can actually be reduced to a differential equation for z. So, in order to achieve that, note that expression in the integrand can be written in the following form. And as this expression stands inside the integration, it's quite natural to require for this expression to be a full derivative. So, and it can actually, it has a lot of chances to be a full derivative, because it's already reminds us a full derivative of some product. So, and we will actually require it to be a full derivative of the following expression. And this gives a certain equation for independent function z. And in fact, this equation is, and this is already the main trick, because initially we had equation which was a differential one, and in this particular case of the second order, and in fact all this approach is generalizable for arbitrary order of the differential equation. But thanks to this Fourier type transformation, or actually in this general form it's Laplace type transformation, we managed to reduce our differential equation for y, which used to be of arbitrary order, to a differential equation for z, which is actually of the first order. And moreover, this equation can actually be explicitly integrated. So one way to see this is to expand this derivative, and to divide, or not necessarily to expand, but to divide each part of this equation by qz. So as a result, we have p over q equal to d over dt of qz divided by qz, which is just derivative of log of qz. With this, we have already almost achieved our final goal, and this equation is easy to integrate, but apparently there is no room on this slide, so let's go on with a clear blackboard.